Evening.
Good evening.
Just as a reminder, we have our exam next time, so don't show up for class in person. It'll be by email again. All right, so let's see if this is showing up on the screen. It looks like it. Told the people in class, look, sunshine. How about that? I can't believe it. It's always so dreary at 7:30 at night. It's nice just to get even a little bit of sun here. So email exam next time, beginning next week. I bet it'll be nice here when we come in. All right, email exam on Thursday. There's chapter 14.
Thursday or Monday?
Monday, gosh, I've got an exam tomorrow, boy. Better get my head together here. Yeah, Monday, chapter 14, during the regular class time. And then, the practice problems are online. Hopefully you've been looking at those. I'll go through a number of those tonight. I just have a short thing to finish from last time, some stuff that won't be on the exam. And, boy, it's on the last chapter of the book, this giant tome of a book, and might actually finish it, right? So, like math and physics are both like that. You've got a sort of a real foundational course in calculus here and in first year physics over there that really plays into a whole lot of the rest of your undergraduate education and even into graduate school. It's a pretty rigorous trip anymore. When I took this, it was 4 quarters, so it was a year and a third, and the books just got bigger and bigger, and oh God, pretty hefty book now. All right, so don't show up for class. Problems all similar to the homework, and most of them similar to the practice exam. It's open book again, open notes, open computer, but you can't communicate with the other students or anybody else. No help from people. Any calculator you want. Online calculator, just not online tutors. Calculator. All right, any questions on the exam? During the regular hour and a quarter for class.
Will it be around the same?
I think I'm gonna try and make a slight bit shorter.
That would be
Sweet,
wonderful.
yeah.
I didn't do the last problem on the previous exam, and I was like, oh my, because it was like 15 points. I was like, oh
Yeah.
no.
Oh, no, yeah. That hurts.
Yeah, I still did fine though. I was just
Good.
like, I didn't get to do that
Good luck, you
problem,
guys.
so I was a little bit upset. I was like, well, that's okay.
I should turn the lights on here. I wonder if they can see online. All right, yeah, unfortunately, we gotta go back to some supporting light here. Well, a couple of problems I wanted to mention at the end of the last section. This will not be for the test. How about this one? Based on what we did last time, suppose we want to find the tangent plane to a surface given parametrically. Maybe I should make a note on this first.
Are these his last
I'm on the
questions?
screen here online, aren't I?
His last 2 homework questions?
Yeah, this would be the last part of the homework questions. This one will be, yeah. Note, so there won't be find a tangent plane of the surface on this exam since I didn't get to it last time. One note, we've been doing surfaces. Z equals f of x, y, right? However, there's another way that people like to write surfaces. You think of taking a little patch of the xy of a UV plane and mapping it into a surface in x, y, z space. We can also generate surfaces parametrically. Leave that stuff with this. In other words, x is a function of u and v. Y is a function of u and v. And z is a function of u and v. With the concept that you have a little patch of space in UV space, maybe it's a rectangle, it doesn't matter, it doesn't have to be a rectangle. Some region here, S, and you map it into XYZ space, and as you do, you can curl it up and twist it around and generate some sort of a curved surface over here where if you hold, say, V fixed at some point V0 and let U vary, over here, this line segment here corresponds into a curve here. You have another line segment here that corresponds to a curve here, another line segment to another curve. And then you can hold U fixed and get these, for each, let V vary, and get curves over here like this, and it fills up. That is, you map each point from here over to here, and this thing just kind of gets twisted around like that. You can generate this surface with two parameters is a nice way to do these. Some people like to do it that way. In this case, let's draw a little more picture here. When you're holding, say, U fixed and you're moving just in V, this one here, you get a vector that's tangent here, which is dz r dv. And the tangent to this curve here is some vector dr du. Right. And now you can do things like find a normal to this surface. How can you find a normal? Well, since these are two tangent vectors, right? The idea is you're taking a tangent to this curve that's embedded in the surface, and you're taking a tangent to this curve in the other direction where you're changing u but holding v fixed. And so these are both tangent vectors. Just like when we took a function of one variable, you said the tangent vector was the derivative of this in the curve. So we're just taking tangent vectors to those two curves. This normal vector here then can be dr du cross dr dv. Right, you take dr du cross dr dv, then it goes by the right-hand rule. Is normal now. Assuming you have derivatives to be able to do this. What that means then is that you can find a tangent plane from a parametrically given surface by computing this normal vector and then taking the point on the plane. And remember, a point in a normal, you can write the plane in point normal form. So let's try that over here. All right, we'll say find the tangent plane to this curve. X equals u squared, y equals v squared, z equals u plus v. A parametrically generated surface in XYZ space at the point, we'll say this is the whole plane here, so this will get a surface that goes out to infinity also. At the point 1, 4, 3, which evidently is on the surface. How can I find the tangent plane? Well, you say the r du, where r is the vector with these three components, then 2u, 2v, and 1, right? The taking partial of these components with respect to U, then I'll take partial with respect to V. And I should point out, this corresponds,
The camera.
what's out of place?
Focus it. It's blurry.
Oh, no. I don't know how to fix that, unfortunately. I guess I can
It's better.
move it, maybe it'll fix itself.
For dr du, wouldn't the middle term be 0 since there's no u?
Oh, I'm sorry. Yes, you're right. This is no U. This is 0. Thank you. 2U, 0, 1. All right. We give extra points for that stuff, but people embarrass me all period when I do that, so. All right. Now, the RDB is 0, 2B, and 1 by taking partial derivatives again. All right. So there's the RDU and the RDB. Now, those being tangent to the surface, you have the normal vector as their cross product. Now let's just write the RDU cross the RDV. But I wanted you to at least see this concept because this is another way people do surfaces, and it's kind of neat, I think, really. So we take the cross product of those, and we can do it pretty easily, right? 2 times 3 minus 3 times 2 is 0 minus 2v. And we take 3 times 1 is 0, minus 1 times 3 is minus 2u. And then 1, 2 is 4uv, minus 0, minus 2, 1 is 4uv. So I'll just take the cross product quickly by hand there. And there is the normal vector. And I should have said, I started to write it over here. This occurs for u equals 1, v equals 2. So now, at this point, 1, 4, 3, the normal vector that we've computed is minus 2v, which is 2, minus 2u, 1, and 4uv, 4 times 1 times 4. 4 times 1. 2, 4 times 1 times 2. Is minus 4, minus 2, 8. All right, that's a normal. Easier, we can call it n hat or something. It doesn't, we can divide each of those by 2 or by negative 2, might be even easier. Suppose I divide those by negative 2 and say a normal is n hat is 2, 1, minus 4, just dividing that through by minus 2. It's still normal, just in the opposite direction, half as long. Now I also have a point. This is my point, x0, y0, z0. So we can use the point normal form, right? For a tangent plane, once we have a point in a normal vector, we can write immediately. A times x minus x0 plus b times y minus y0 plus c times z minus z0 equals 0. Where a, b, c are the components of the normal. And x0, y0, z0 is the coordinates of the point. This then becomes, let's see, 2. Now you see what I wanted to simplify. It'll get easier numbers up here. 2 times x minus 1 plus 1 times y minus 4 plus minus 4 and c minus 3 equals 0. All comes out to be 2x plus y minus 4z. Then I've got 2 minus 4 is minus 2 plus 12 is 10, and over the other side becomes minus 10. So a little bit of algebra there with that tangent plane.
the middle, when you got negative 2v, negative 2u, how did you get those values again?
You just have to know what the map is. It's, generally what you do is you say we had x equals u squared, y equals b squared, and z equals u plus v. And what you then do is say at the point u equals 1, v equals 2, you plug these into find x, y, and z, and so you got x equals 1 squared is 1, y equals 2 squared is 4. And z equals u plus v. Wait a minute. Oh yeah, u plus v, 3. 1 plus 2 is 3. So that's what you usually do. You say, here's this point uv. If you instead start with the 1, 4, 3 and have to work backwards, then you have to invert these equations, right? U and v is functions of x, y, and z, and that's not always so easy. But sometimes it works. So better to start with u and v. All right, so it's just by plugging in. All right, so that's parametric surfaces.
That, the final thing you box, that's the tangent plane.
Yes. Yeah, so it has the standard form, ax plus by plus cz equals v is a plane. That's the standard form for a plane with normal vector 2, 1, minus 4. In this case.
You wrote the is equal to the cross product at the second term. Bottom should be a v, right? There's 2 u's. Yeah. Yeah, right.
Oh, yeah, the RDU cross the RDV. Sorry
Okay.
about that. Yeah.
No, you're fine. Just making sure we're paying.
Yeah. See, I told you if I paid you money, I'd have it out all night. All right, now as a special case, what about a surface z equals f of x, y?
Can you move the camera, please?
Yeah, thank you. If you have this special easy case, this corresponds to the parametric surface easy case. X equals u, y equals v, z equals f of uv. So you can compute the thing the same way. N then becomes, since x equals to u, you just have minus dz dx. Since y equals v, you've got minus dz dy. And then 1 for this one. Gives you a normal vector. So we can, let's say, find the tangent plane to z equals x squared plus y squared at the point x equals 1, y equals 2. You can do the same kind of thing easier. Now the normal vector is just immediately dz dx is 2x, dz dy is 2y, and then minus 1. And at x equals 1, y equals 2, you have to compute what z is. Z is equal to 1 squared plus 2 squared is 5. And so you take the at x equals 1, y equals 2, the normal vector. becomes -2, -4, 1. And then this is your A, B, C. These are your X0, Y0, Z0. And you can plug those into the polynomial form. The plane is the same equation, the point normal form, A times X minus X0 plus B times Y minus Y0 plus C times Z minus Z0 equals 0. Let's see, so A is -2, implies X minus the X coordinate, which was 1, plus B -4, multiplies Y minus the Y coordinate, which was 2, plus C, which was 1, times Z minus the Z coordinate, which was 5, 0. And so I multiply this out, -2X minus 4Y plus Z. And I've got +2, +8 is 10, -5 is 5, put over the minus, other side is -5. That's that one. So there's a tangent plane to one that's just given in the more common form, Z equals F of XY. Can just be written that way. And then finally, suppose you want to find the surface area when this thing is given parametrically. X a function of UV, Y a function of UV, Z a function of UV. I can't, the book presents this very nicely, but they don't even have any problems on it. Maybe I'm just missing something back there, but I do actually have, I think, at least one problem in the notes that I put out there for you, but I'm not assigning it. Now, what do we have for surface area? Can be gotten like this. You've got a surface and you break it up into patches. Again, according to fixing U and fixing V. And what you have here is this vector here that if you try and make a tangent plane over a particular surface patch like this, using two vectors, and this vector can be the vector, if this is with U equals U0, a parametric curve within here, and this curve is a parametric curve V equals V0 within the surface, then this vector here looks like dr du is tangent to the plane, and then times delta u, say delta uk for the kth piece here. You partition it up like this. The idea is it's the run times the rise. And then similarly over here, what you've got is dr dv. Oops. This should be v fixed here. I wrote it backwards. V equals v0. This is u equals u0. When v varies, and when u varies, you take dr to u, the slope times the run. When v varies, you take the slope times the run in the v direction. With dr dv delta vk for the kth piece. And now, what's the area of the little plane up here that sits over this? Call this area the area AK, the kth piece. Well, if you remember the area, this is a parallelogram. Right, since it's got two vector edges. And you make a parallelogram by putting these parallel. And the area of a parallelogram is the absolute value of the cross product of the vector edges, if you recall, right? So that would be this one cross this one. The R du, I said absolute value means length. Length, so the R du delta UK cross the R dV delta VK. But that's just the length of the R du cross the R dV times delta UK to VK. I've only given it one index as though you're partitioning in one direction, but the idea is this is like the ith increment in the u direction and the jth increment in this one, and it's the kth piece up here, indexing them just with one index. So that's the area of the kth parallelogram, and then the surface area can be approximated by the sum k equals 1 to n, the number of parallelograms, indexing both directions. The area of each parallelogram, right? AK, and take the limit as n goes to infinity. If you add up the areas of the parallelogram, take the limit as n goes to infinity. We'll define that to be the surface area, partly because if this thing has continuous derivatives, you get the same result regardless of how you partition it. So it must be what we want to call a surface area. Now, what this comes out to be is the limit k goes to, or n goes to infinity of the sum k equals 1 to n. This stuff, right? Because AK, that's this one, AK. Yeah. The RDU cross the RDV delta UK the VK. All right. So we make this definition. The idea in mind, it doesn't matter how you partition this or what points you pick in the partition. And actually, these partial derivatives, I didn't want to write out all the notation. They're evaluated at some point, like maybe at each corner here, like I've shown it. So maybe you plug in to get the partial derivative at this one corner, and that generates a parallelogram over the surface. And this is the area of the parallelogram relative to evaluating these at some point in the surface, such as the corner. Now, what is that we've generated there for the surface area? Think about it. We have just defined the surface area through the definite integral, right? Limit sum delta UK delta VK is a double integral of whatever's in here as a function of u and v. So it's the double integral over the region, I guess they call it S in UV space. The RDU cross the RDV. Okay. So there's another way to generate surface area. And the surface area we already did, once again, just like with the tangent plane, if x equals u, y equals v, and z equals f of uv, in the special case, this reduces to what we had before, that the surface area is the double integral over the plane region R, because the plane region R is S is the image of, oh, I'm sorry. This is the image in UV space of the actual surface, the actual domain of the function. this reduces to the integral over the domain itself, since S and R coincide if you do this. And this thing, the length of dr dx cross dr dy dA, now in xy space, then becomes the double integral over R. And this one, when you compute it, it turns out that's what we did last time, if you think about it. It's the length, well, it's the length of minus dz dx minus d, when you compute the cross product, minus dz dy 1 dA. And that is just the surface integral we did before. It's the double integral over the region of the square root of dz dx squared plus dz dy squared plus 1 dA. So there, what we found out is that more generally, if you were at a parametric surface, x, y, and z all as a function of u and v, then this is the formula for surface area. And in a special case that we write a surface like this, then we get the formula we had last time. So this is a nice generalization of what we did. You can maybe see again in advanced calculus, but it allows a little more generality, as you can see, since this is a special case of that. All right, and that finishes the section, and I didn't even mean to spend that much time on it. Any questions on all that you want to look at? We'll go ahead and do the review then.
The bottom where the vector, you have like an absolute value sign on the
Oh, yeah, put
right
it,
edge. Is that-
yeah, I forgot to put it on this side too, thanks. Yeah, it's the length of this vector, right. So that's all written up in the book too, and also in my notes. If you want to see that some more there. All right, so surface area, I think, is one of the harder things, this concept of, taking a region in UV space and then tapping it over to the surface in XYZ space. Kind of an abstract thing. All right. Well, what would you like to look at tonight? Anything in particular of the problems in the book or the problems in the practice set?
Can you do number
The
4?
bottom actual test will be much shorter. What?
4?
4? Okay. Let's find the volume.
I don't know. I heard
Okay, let's try it anyway. The volume of the solid above the surface, and this tells me to remember some of these things from previous chapters, doesn't it? I'm sneaking it in. Z equals 1 minus x squared minus y squared, and below Z equals 1. Within the cylinder, x squared plus y squared equals 1. How about that? One of the big tricks to being able to do these is actually to sketch them. Then you understand what it is you're doing. See the equation, it's hard to tell. Let's try and sketch. What does Z equals 1 minus x squared minus y squared look like? You should be able to draw this now. Oh, outstanding. Yeah, you got that right away. So you think of it this way. This is how I do it. Z equals ax squared plus by squared was a standard equation. What kind of surface is that? What do we call it? Actually, we usually wrote it this way. X squared over a squared plus y squared over b squared. Maybe this is elliptic paraboloid, right? It had elliptic cross sections and parabolic cross sections, right? And so it looks like this. Elliptical cross sections there. There's a parabola and the other two. Now, if I put z equals minus x squared minus y squared, that's an elliptic paraboloid upside down, right? Z equals minus x squared minus y squared is a special case of this with a equals b equals 1. And flipped upside down. Furthermore, since a and b are equal, it's a circular parabola. You get circular cross sections. So it's this one upside down. And all the cross sections this way are circular. Now, what happens when I stick the 1 on there? That just adds 1 to every z coordinate, right? So it slides it up 1 unit. Z equals 1 minus x squared minus 1 squared. Moves this up 1 unit. Translates the proper term. Now what you have is exactly what he said, is a dome upside down. Like that. Here's this one. X, Y, Z space. All right. Now we want it below. Suppose I put Z equals 1 on there. Don't even need that.
The 1 just be your top C bound.
Yeah, oh, I'm sorry, I do need that, yeah. So now I put Z equals 1 is the plane up here that just touches the top of this thing. So it's topped by the plane, touching it right here. At 0, 0, 1, we can compute by plugging in. I plug in x equals, y equals 0 and get Z equals 1. And now we say inside the, I gave you a hint there, x squared plus y squared equals 1 cylinder. Draw that in another color. There's no z in there, right? X squared plus y squared equals 1, we recall is the unit circle in the xy plane. 1 and 1. So what is it in xyz space? It's this extruded arbitrarily in the z direction. So you take the unit circle, which is right down here, slide it up like that, and you get a unit radius cylinder, like that. So you want to be inside the cylinder, above the paraboloid, circular paraboloid, and below the plane z equals 1. There it is. It's over this little thimble-like thing and below the plane and inside the piston cylinder there. All right, now we know what we're supposed to integrate over, right? That's always a good thing to have. And by the way, this, when you put in, when you try and find what's this intersection down here, you do that, you put in z equals 0, because right, it's the trace in the z equals 0 plane. So 0 equals 1 minus x squared minus y squared gives you the unit circle. And so this circle here coincides with the bottom of the cylinder, actually. Just by setting z equals 0 to find its trace in the y plane. Now we can integrate, now that we know what we're doing. So the volume, recall, is just the triple integral of 1 over the solid G the book likes to use in letter. I call this solid G. And what do I have to integrate over to do that? Well, when I look at this, this looks like probably cylindrical coordinates, where it would be a whole lot better than x, y, z coordinates, right? Possibly spherical coordinates, but because there's a cylinder in there, I think cylindrical coordinates. Cylindrical coordinates. I don't know if I gave that hint up here or not.
Yeah.
Okay, yeah. Oh, I said polar coordinates. Okay. Yeah, so you can, right. If it says polar coordinates, then you have to use the other formula. I mean, this is right. I'll give you full credit for that, using cylindrical coordinates. But I said use polar coordinates, so let's say this, that you can also find a volume over the XY plane and below a surface, or between two surfaces, by taking, the double integral over the plane region that's the projection of the top function f of x, y, z minus g of x, y, z, the bottom function. So that's the volume between two surfaces, a top and a bottom, dA. And this is what you get if you use cylindrical coordinates anyway. The inside integral would degenerate to that. All right, and so if I use polar coordinates, then look at the region of projection here, which is the unit circle. A unit disk, x squared plus y squared less than or equal to 1. To integrate over that, I have to let r go from 0 to 1 and theta go from 0 to 2 pi. Recall. The top surface is now the plane up there, so that's equals 1. And the bottom surface, if I rewrite it in polar coordinates, z equals 1 minus r squared, right? X squared plus y squared is r squared. So that's the circular paraboloid. And then for dA, recall for polar coordinates, you need r dr d theta. There it is. There's the integral I have to do to evaluate this volume. It's integral 0 to 2 pi, integral 0 to 1. Aren't we fortunate, right? 1 minus 1 cancels out. You have to integrate r squared, r dr d theta. Since there's no theta in here, you can pull the d theta through. Product of integrals, integral 0 to 2 pi d theta, integral 0 to 1 r cubed dr, and it's pretty easy then, right? 2 pi for the first integral, times r to the 4th over 4, evaluated 0 to 1, this just comes out to be pi over. Okay.
We did that cylindrical, you wouldn't count it wrong. Got the same.
No, since cylindrical is polar coordinates add z, I'd still count it on it. You know what happens if you do this in cylindrical coordinates? You put v equals triple integral of 1 dv, and then you say, what do you have to integrate over? You integrate over, you rewrite that by the projection theorem as the double integral over the region of projection, which is the same disk. Integral from the bottom surface to the top surface, so it's bottom surface to the top surface, dz, dA, and then at the next step, since you're just integrating 1, you just get top minus bottom, and this. So if you write cylindrical, then you write this, and it comes to this in the next step. This would be cylindrical, and then in polar coordinates, you get this. And I would only count that still because it degenerates to the same thing. So you've got all the steps and more. Those are kind of tricky sketches, but they're part of practice over time.
Can you do number 9?
Sure. Find the domain of range. We didn't do too much like this, but I usually emphasize this a little bit more. This isn't very hard, is the good thing. What is the domain? That is all x and y that can go in the plane region. The range, the values of z that can come out of the function of two variables, f of x, y, equals inverse cosine x minus y. And what you do when you look for the domain of this, there's something called the natural domain, which means in algebra, you don't want any divisions by 0 or even roots of a negative number. So you look at the natural domain of this algebraic expression and you say, oh, that's just all x and y, so we call that R2. meaning the real numbers, Cartesian product with the real numbers, the set of all ordered pairs x, y go in, right? Right, the real numbers, Cartesian product, the real numbers are all ordered paired with the first element is a real number, the second element is a real number. Which means this, all real number pairs x and y. So that's the natural domain of this algebraic expression, but now that I have a function of that, which is only defined if I call this u, for u between -1 and 1, right? The cosine, if you remember its graph, looks like this. It's u versus z equals our cosine of u. Our cosine is only defined between -1 and 1, so the domain of this one, u between -1 and 1, which equivalently is -1 less than or equal to x minus y is less than or equal to 1. Which now if you multiply by -1, then you have to switch the direction of the inequality. You have 1 greater than or equal to y minus x greater than or equal to -1. I just multiply through by -1. No, it's still the same. Yeah. Okay, so I multiplied through by -1. That means I have to switch the inequality directions. Which also then you can write it in the other order, -1 less than or equal to y minus x less than or equal to 1. And now if you add x outside, this is x minus 1 less than or equal to y less than or equal to x plus 1. And so you look at the boundaries. This is x minus 1. The boundaries are the lines of the equality there. So boundaries, this region, are y equals x minus 1 and y equals x plus 1. So I can sketch those because that's y equals mx plus b. This is slope 1 and y-intercept -1. It looks like that. This is slope 1 and y-intercept plus 1, goes through here at 1. Looks like that. And then I allow equals. If I don't allow equals, then I have to draw dotted lines, meaning the boundary isn't included. But since I allow equals, I have to draw solid lines, meaning this is part of the domain. And then what happens is whenever you're dealing with continuous functions like this, the continuous function, because right, it's polynomial. This is a continuous function. It can't just jump over this, or even this one. This one can't just jump over 1 or below -1. It has to move continuously through it, which means that this can't change, can't stop satisfying the inequality except at the boundary, right? It has to move continuously through equality. And so what happens is all the points between these boundaries are either satisfying these inequalities or not satisfying it. You just check one point, you plug in 0, 0, for instance. Is x equals 0, y equals 0? Let's see, you get 0 is between them. So 0, 0 is satisfies the inequalities. It follows that all these points in here also satisfy, because in order to satisfy the inequality here, and this function changes continuously, it can't jump over 1. It has to move continuously through 1, so you have to go across the boundary where this one, where y equals x plus 1. And then you check the point out here, maybe -2 for y and 0 for x, any easy point you want. 0 minus a -2 is 2. That's bigger than or equal to 1. That's not in the region, so you don't shade this part. And the same out here, you pick your favorite point, 0, 2. Plug that in, and 0 minus 2 is less than -1. So you don't shade this region. But between the boundaries, you either shade everything or you leave it unshaded. All you have to do is check one point in each region, and you find out this is the domain between those two lines. that's how you find the domain and range. I'm gonna only give you continuous functions like this, in which case you just find the value. You write the inequalities, whatever they are, find the boundaries and then checkpoints in between the boundaries and in all the regions.
Did you use a -2 on the bottom? Like you did 2 at the top and then -2 at the bottom when you checked it?
Yeah, I did -2. You can pick any point you want that's down in this region. Or they'll all either satisfy or not satisfy.
Yeah, I don't know what those fancy R's mean.
Oh, I'm sorry, that stands for the real numbers, yeah. Let me do this. If I take the Cartesian product of the set 1, 2, 3 with the set AB, what's this? You should pick up this notation this semester. It should be before the semester. What does that mean? After the famous philosopher Descartes, who said, "I think, therefore I am." He was also famous for, all his arguments about God and as well as being one of the pioneers of analytic geometry. So you see his name in here a lot. It was analytic geometry, that made coordinates possible in algebra, whereby you could develop the calculus. So he sort of helped set the stage for Newton and Leibniz to come along by making coordinates in algebra possible. The Cartesian product is the set of all ordered pairs, where the first element comes from this set and the second one from this set. So it'll be 1A, 1B, 2A, 1, 2A, 2B, 3 with A, and 3 with B. That's the Cartesian product of these two sets, just all ordered pairs where one comes from this and one comes from this. Now R, written boldface with 2 bars here, is all real numbers. That means all numbers that can be written in decimal form is the way to think of that. All real numbers. So what does R2 mean when I write that notation? That's short for R Cartesian product with R, which means the set of all ordered pairs X, Y, such that X and Y are both elements of the real number set. This means element of, introducing lots of notations. But it's all ordered pairs of real numbers, X, Y. That's what R2 is. It's the plane, the XY plane. What books like to do, there's a very popular calculus book by Rogowski that likes to use this notation. The region 1, 2, Cartesian product 4, 6 in the XY plane. What is this? This means all ordered pairs where X comes from this set and Y comes from this set. So you take X between 1 and 2 and Y between 4 and 6. It's this rectangle here. All ordered pairs where the first number is between 1 and 2 and the second one between 4 and 6. So you'll see this kind of notation even in other calculus books. If they want to take a rectangular path, they'll take this interval, Cartesian product, this interval. It's not cross product, it's Cartesian product. I hope that notation will help you in mathematics, because this is used really, really a lot in higher mathematics. In fact, this is called the Euclidean plane. And if you take Rn, this is Euclidean n space with real Euclidean n space. There's also a complex. And so because of that, this is used extensively. So things in Euclidean space.
Number 11.
Yeah. By the way, you guys, feel free to, if you can't make my office hours, send me an email. I can probably meet you at other hours. I meet people at night since it's virtual. I can just sit at home and meet you. I don't have to drive out here or something. All right. So if you get stuck, let me know. Or if you have a short question, just ask an email answer. But if you want a longer question, took a whiteboard home from my office, so I can do things on the board at home. All right, so this is where I usually forget which question number it is, but I remember this time it's 11. Talk too long. All right, sketch the domain. I almost did this one just a little bit ago. Sketch the domain and expresses an iterated integral in the opposite order. Catch and write as an integration in the opposite order. This is a trick that sometimes comes into play when you have a difficult double integral. Sometimes you just don't know the antiderivative to be able to do this, right? You're trying to do this one, for instance, integral from 4 to 9, integral from square root y to 3, some function f of x, y, dx, dy, and maybe I just can't integrate this thing, or maybe after I get it and evaluate it here, I can't integrate it at the next level. How can I rewrite it in the other order? Sometimes you can figure out how to integrate it if you just write it in the other order. The best way to do that actually is to write the sketch and then you can see what to do. So you say this is a double integral over some region, f of x, y, dA. You don't have to write this intermediate step, but the region is then the region R. This is what we call a type 2 region, right? Because y goes between two fixed numbers, c and d. The outside integral is always fixed numbers. So it goes between 4 and 9. And x goes between two functions. A left function, x equals square root y. Remember this type 2 region? If dy is on the outside, it's type 2. If dx is on the outside, it's type 1. Whichever one goes between the constant endpoints, the other one goes between two functions. And then this one is the function x equals 3. This is the right boundary. So I draw x equals 3 on the right. That's just a vertical line. And I draw x equals square root y on the left. Well, that's pretty easy. It's y equals x squared. And it goes up like this. Oops. Too fast or too slow. It goes up about like that. And it turns out it intersects right at 9. You can check it by finding the intersections, right? Because this is, after all, x equals square root y. And this is x equals 3. And you find where do they intersect? You set them equal, right? You said 3 equals square root y. Same as equal, and equivalently, that's y equals 9, right? So it's evidently the point 39. All right, and now what we have is this is the left function, this is the right function. This is the beginning right here, and this is the end, so it's this region right here. R. That's the sketch. You think of it as type 2 region, y going from C to D, x going from a left function, x equals square root y, to a right function, x equals 3. Now, how do I write it in the opposite order? This is also a type 1 region, right? Where you have x going from a fixed number to a fixed number, and y going between a bottom function and a top function. And so you just have to figure out what the integration limits are. You draw the same region here. Square root y, there's that one, goes over to 3. This is a 4. So now you have to find this intersection point. This is the intersection of y equals 4, bottom line, with the curve x equals square root y. So you can set those two equal. These together, you get x. This one says x squared equals y, and this one says y equals 4, tells you x squared equals 4. Tells you that x must be equal to 2 at this point. Find their intersection to find the x value. And now I can say, oh, this is going from fixed numbers on the x-axis, 2 to 3, with this at the top, rewritten x equals square root y is y equals x squared, and this at the bottom, y equals 4. Now from the type 2 region, I say that this is now equal to the double integral x on the outside going between the constants 2 and 3, min x, and the max x, fixed numbers. And then the bottom surface, we observe is y equals 4, so we just put 4. The top surface is y equals x squared. You have to write y as a function of x this time. You take x equals square root of y and rewrite it as y equals x squared by squaring. Squared. There it is. dy in here. So integral f of x y, whatever the integrand was, dy on the inside, dx on the outside is a type 1 region. Who's going from the bottom curve to the top curve, and then the min x to the max x. So this is what I want to see in there. And sometimes this can be easier to integrate, right? Just depends.
Number 13.
Sure. What would I have? D be the domain bounded by the x and y axes and the line y equal 2 minus x. The x-axis is y equals 0. The y-axis is x equals 0. And the line y equals 2 minus x. In the plane, sketch the region. Sketch the leaders. And for the density function, mass density, rho of x, y is just equal to x. In general, can depend on both x and y, is why I wrote it that way. Find one, the total mass. This lamina, they sometimes call it plane region. About that, remember mass? Mass is just the double integral over the plane region of the density function. Popular letters for that are rho or delta. Sometimes I'll use rho for mass density and delta for weight density separately. It depends on what they're. All right, so now what we need to do is we've got the double integral of x dA. But what does this region look like? Pretty easy, right? The two axes and y equals 2 minus x. What does that look like? Let's rewrite it. Because y equals minus 1 x plus 2. So it's got slope minus 1 and y-intercept 2. 2. Then it goes down 1 like that. It must intersect here. Right? Slope minus 1 means it goes through that point. There is the third boundary. Y equals 2 minus x. And we must be talking about this triangle. How do I write that triangle in integration over that triangle? I can do it either type 1 or type 2, right? I can go from 0 to 2 and then y between this bottom and this top. Or I can let y go from 0 to 2 and go between this right and this left. Usually it's easier to think calculus 1, type 1 region. So let's let x be the constant and points go from 0 to 2. Y now goes from the bottom surface, right? So this is the min x, max x, the bottom curve, and the top curve. Y is a function of x. The bottom curve is y equals 0. The top curve, y is a function of x, is y equals 2 minus x. And then dy dx. That will give me the mass. Let's see if we can evaluate that now. That's integral from 0 to 2 on the outside, and then this one, if I integrate x, I get x squared over 2. I need to plug in 0 and 2 minus x. Then I'm going to integrate with respect to x. Now it's integral from 0 to 2 of 2 minus x squared over 2. This was not x squared over 2, it's, I miswrote this. The integral of x, it's integral with respect to y, this would be xy, sorry about that. Partial integral with respect to y should be xy. So I have x times 2 minus x. When I plug in 2 minus x, I get this, and when I plug in 0, I just get 0 dx. So that's the integral from 0 to 2 of 2x minus x squared. That's an easy one, right? So I just say, oh, that's x squared minus x cubed over 3. Plug in 2 and 0 and take the difference. I get 4 minus 8/3 is 4/3. So there's the mass. The second part is to find the center of mass. So the book will call it the center of gravity, which coincides with gravity's constant. Center of mass has two coordinates. X bar is the double integral of x times the density function, PA, over the region. This is sort of the average position of mass. And then it's all divided by the mass. Double integral, just take the x out. Well, how do I write this down? It's easy. All I've got to do is write down what I wrote before and stick an extra x in, right? So this is the same double integral I had before, 0 to 2 and 0 to 2 minus x. And the same integrand, x, except multiplied by x, so x times x, dy dx. That's a good thing, you can just write the same integral and stick an x in it. And the bottom now, we already calculated it's 4/3. All right, so 1 over 4/3 is 3/4. Then I've got the integral from 0 to 2, integral from 0 to 2 minus x, x squared. That's pretty easy. X is a constant in this partial integral. I can pull it out here, right? X squared dy dx. So you can pull the constant out. Well, the integral from 0 to integral of 1 dy is just y, and you plug in, right, this is just y, plug in the top and bottom and take the difference. So it's just 2 minus x. Right? Plug in 2 minus x, plug in 0 and subtract. So this is 3/4 the integral from 0 to 2 of x squared times 2 minus x dx. Evaluating this inside integral quickly. Let's do it carefully now. 3/4 the integral from 0 to 2 of 2x squared minus x cubed dx. Integral 2x squared gives me 2/3 x cubed. Integral x cubed gives me x to the 4th over 4. Plug in 0 and 2 and take the difference. But I've evidently got, oh, and I forgot to, oh no, I got the 3/4. 3/4 times, let's see, 16/3 from this one when I plug in 2, minus 16/4 is 4 when I plug in 2 in this one, and then that's from the top end point, and 0 and 0 from plugging in the bottom end point. Well, let's see, that's 12/3, 16/3 minus 12/3 is 4/3, that times 3/4 is 1. So evidently, X bar is 1. The idea here, you can balance it right on this point. Why does it balance here? It looks like it wouldn't, right? But the density function is equal to X, so it's a little heavier on this end than on this end. There's more area over here, but this is 0 density here, and this is density 2 over here, density 1 in the middle. So that this heavier end over here, heavier, denser material over here is balancing the lighter material over here. Now we can compute Y bar the same way, right? Y bar is just the double integral of Y times the density function. Okay, over the same region and all divided by the mass. So you write the same integral you did before. 0 to 2, 0 to 2 minus X. This is now X times Y, dy dx, all divided by the density, which was 4/3, mass, which is 4. Maybe I'll just say dot, 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 and I'll give you the other coordinate.
Just leave those two coordinates like separated or take the,
Yeah, you can take the X out of here and do it like this if you want.
I'm saying like the two answers we get, we take the magnitude of those, or do you just?
Oh, then you take, the answer is X bar, Y bar is the center of mass, equals the one we got there, 1, together with this one, whatever it is. That'll be the
Okay.
bar. So X bar, Y bar is the answer. That's the center of mass. And if you took this thing, tilt it on its side, that's the point you can put your finger in the balance. In uniform gravity. We can finish this if you wanted. I have time for one short one, I think, and then I always stay a little bit after if you want tonight.
Number 12, for your answer, you have 7 pi over 2, let's say 1. What's the second part? For my answer, I got just 27 pi over 2. I don't know where the other chunk came from.
Okay. Cut that up quickly, huh?
Maybe just like the bounds, maybe instead of 0, I should have had a different bound, but I don't know.
All right, so number 12, I said, you convert to polar coordinates. This one is easier in polar coordinates. Integral from oh, I know what, this is a tricky one. -3 halves to 3, I can't do this quickly. 0 to square root, but it's a good one to get started, 9 minus x squared. X squared plus y squared dy dx. This is screaming for polar coordinates if you think about it. Because what is this in polar coordinates? R squared, yeah. They just reduce it to R squared. And what is this reduced to in polar coordinates? This, the integral reduced to in polar coordinates. Well, this top end point here is y equals square root 9 minus x squared. Right? If you square both sides, you got y squared equals 9 minus x squared. Add x squared to each side, you got x squared plus y squared equals 9. It's another circle, right? Circle of radius 3 at the origin. And so this is looking for polar coordinates too. However, y equals the positive square root restricts you here to y greater than or equal to 0. So it's actually a semicircle. Half of this with y greater than or equal to 0. So that's the top surface is a semicircle. The bottom one is y equals 0. And so what you've got is on the top, this y equals 9 minus x squared, half of the circle of radius 3. So it goes between -3 and 3. Then in the bottom, you've got y equals 0. This is a type 1 region, right? Y on the inside, x on the outside. And now x goes from -3 halves to 3. So you're actually coming from right here, -3 halves, out to 3 here, and you're looking for integrating over this region. So this actually even though it's in some sense screening for polar coordinates, it's, not easy in polar coordinates. If it was just a circle, if I went from -3 to 3, this would be much easier. What we have to do in polar coordinates is break this up into 2 pieces. And this is what you can do. This, you probably did one of these 2 parts, so you have to think of it as a simple polar region from a ray theta equals some angle, like theta equals 0 here, to a ray theta equals some other angle. Where does this go? Well, if this is -3 halves and this is 3, not 3, this is 3. Then this is 1/2 of this one. Oh, that's a 30, 60, 90 triangle, right? Pi over 3, 60 degrees is the angle. That makes this angle here, theta equals 2 pi over 3. So in a simple polar region, we're going from an inside curve r equals 0 to an outside curve r equals 3. This part here, we could break this into 2 regions, call this R1 and R2. And we could say this integral here is equal to the double integral, grew up here before, is the double integral over R1 of R squared dA plus the double integral over R2. Oh, that's the side of it. 3. Double integral over R2 of R squared dA. I'll do an integral over this. Now, what is this curve here? When I do this side, the inside is still R equals 0, but the outside curve is this one. What is that? Well, this curve is x equals -3 halves, that vertical line, is also r cosine theta equals -3 halves, which is r equals -3 halves secant theta. R is a function of theta. So that's what you do for the for R1. In a simple polar region, you let theta go from the min angle to the max angle, which would 2 pi over 3 of pi. That's this angle. This is not it. So I'll go from 2 pi over 3, the minimum angle, pi, the maximum angle. Inside curve, r equals 0. The outside curve, r equals this one, -3 halves secant theta. R squared, and dA is r dr d theta. That's the first integral. Then the second one is easier. Theta from 0 to 2 pi over 3. Outside, r from 0 to 3 on the inside. So these are both constants. It's easy. And then integrand r squared, and dA is r dr. So you have to do these 2 integrals. Okay, I'll just put equals dot, dot, dot. And so if you do both of them, then you get that answer.
Thank you.
Yeah. All right, so stay a little bit longer if people want, otherwise I guess we're done. First questions on the test, contact me if you have more questions.
Available weekends,
Oh, some on Saturday.
some
I mean, I'm gonna only check it once per day, so you might lag me Saturday and one next year.
You just put your address on there. You just put your address up there.
Oh, there we go, yeah.
Knock, knock. I brought questions. That's dedication right there.
Thank you, everybody.